we're going to be looking at more types of forces today. Jordan, we're going to be, again, doing some more free body diagrams, more winner minus loser, and it's usually going to be either I'll give you the acceleration and we'll find a mystery force, or I'll give you the mystery force and we'll find the acceleration. Again, I would encourage you not to be working on homework during the lesson. That would be silly. Let's talk about air resistance. What is air resistance? It is a force. It's the force of air molecules bumping into an object as that object is moving through the air. The faster you move, the more molecules you bump into, the bigger the force. Here's the key. The force of air resistance always has the direction opposite to motion. So in your free body diagram, when you're asking which way is air resistance, which way are we moving? In the opposite direction. Not which way are we accelerating, which way are we moving? Air resistance will be in the opposite direction. So example 1 says, draw free body diagrams or force diagrams for each of the following. Oh, we got more people here showing up late. Again, we're going to draw a free body diagram for 3 situations, okay? A ball being thrown, what I mean by that is while it's in my hand on the way up, and then situation B, a rising ball after it's left my hand on the way up. Situation C, a falling ball. And in B and C, they also want me to include air resistance. If I don't tell you to include air resistance, you can ignore it. But if I do tell you to include air resistance, we'll put it in. This is about the limit of, I've told you before, air resistance is really tricky, Jordan. You need calculus to really calculate it properly. This is about our limit. We can calculate it in kind of snapshots, but we're not going to be able to crunch it from scratch. So this is a job for a free body, because they told me to draw a free body diagram. Although, you know what? They gave me a picture. I'm going to label the picture. What are the forces in situation A? What are the forces on the ball? Get the obvious one. Hello, something weird happening there. There we go. Let's come back here. And there's 2 ways to write gravity. If I just label it, it's the force of gravity. You can put an FG. But now that we know the equation for the force of gravity, what's another word for the force of gravity? Starts with letter W? No, now. I usually just put the actual equation there because that's what I'm going to crunch quickly anyways. What else? Okay, I agree. You could call it force of throw, force hand. You could maybe pretend it was a normal force because your hand acts like a surface, but let's not overcomplicate it. Force of hand pointing which way? Oh. Bigger, smaller, or the same size as mg? Bigger. Can it be smaller? Watch. I will show you an example where the force of the hand is smaller right now. Watch, watch, watch. Did the ball leave my hand? It has to be bigger so that when I open my hand, the ball will keep going because I've given it briefly a bigger acceleration than gravity. It's got some momentum. So I agree, and I'll exaggerate it so it stands out. And that was dumb. I'm writing over the arrow. How about let's put F hand. There we go. Now, while it's in the air, on the way up, look up everyone, on the way up, not on the way down, on the way up, after it's left my hand. What are the forces acting on it? Get the obvious one. Okay, which way? What else? Well, it says in brackets to include air resistance. Which way am I going to point the air resistance force? Which way is the ball moving? Air resistance acts in the opposite direction of motion. You could like try and smoosh an arrow on top of the arrow. I rarely do that. It's too confusing. So I'm going to put here F air. And I'm pretty sure air resistance is smaller than gravity. I think gravity still dominates. C. And I think that's it, right? C. On the way down, what are the forces acting on it? Get the obvious one. Which way? What else? Does it want me to include air resistance? Okay, which way will air resistance be this time? Yeah. Bigger, smaller, or the same size as mg, and how do I know? What if it was bigger? I disagree. The ball wouldn't be going up. Wouldn't stay still. Slow down. That's what the parachute did for me. When I opened my parachute, air resistance was larger than gravity, which is why I slowed down. I didn't come to a stop. I didn't start going up, but I slowed down. Eventually, I reached an equilibrium point where air resistance was the same size as gravity, and my new velocity was survivable when I hit the ground. But here, I'm pretty sure it's smaller. Look at this second diagram here. How is it possible, this is what example 2 asks, how is it possible for the ball to be going up when all the forces are pointing down? Are we wrong? How can the ball be going up when all the forces are pointing down? And this has to do with something I've ranted on a couple of times already about what do Newton's laws tell us. Okay. Is our diagram correct? Jaden, is the diagram for B correct? Say it out loud for my YouTube video. Jaden's nodding, YouTube. Yes. So it must be possible. So the question is, how? Yeah. It's traveling up. Which way is it accelerating? Look at the free body diagram. Which way must it be accelerating? Look at the free body diagram. Which way are the unbalanced force pointing? Down. Which way must it be accelerating? It must be accelerating down. So if it's traveling up but accelerating down, how will that behave? Of course it's good. Yeah. All that's really saying is on the way up, the ball must slow down. Yeah, totally works. So Newton's laws tell us direction of A. What's A in abbrev for? Thank you. Not V. They don't tell us the direction of velocity. This goes earlier. I can't remember if it was Ronan or Parker, but somebody made a comment, and I said, you're confusing acceleration and velocity. Newton's laws tell us the direction of the acceleration. They do not tell us the direction of the velocity. Velocity's up, no problem. Which way are we accelerating? Down, because we're slowing down. So that's totally good. Example 3, in diagram C, if the ball is speeding up, write a net force equation. Okay, who's winning? Who's losing? What does winner minus loser always equal? And you'll know that somebody asked me yesterday, they said, Mr. Dewick, you use mg sometimes and fg sometimes, and I realized I probably use fg in the equations so that they're all f's, but I use mg on my free body diagram. You could certainly on this line have gone right away to, I know that F, the force of gravity, is calculated by mg. So as far as I'm concerned, I can either tell you the air resistance, and you can find the net acceleration using Alex's theorem, divide by m, or I can tell you the acceleration, and you can get the air resistance by itself. Yeah. I did not find a calculator here yesterday. I can give you a loaner, though. I like example 4. I like example. This is a nice question. I can't remember if I put it on a test, but I also like it because I have jumped out of an airplane. I mentioned I jumped out of an airplane? I've jumped out of an airplane. So let's look at a parachutist. They free fall for a time, and then they open their parachute. His new upward acceleration is now 1.5 meters per second squared. Why is his acceleration upwards? More specific. Why would he be accelerating upwards? Slowing down. Okay, you don't speed up when you open your parachute. If you're moving down, but you're slowing down, which way are you accelerating? Upwards. Let me say that again. Which way are we accelerating, everybody? Which way are we accelerating, everybody? Which way is the bigger arrow going to be pointing? Upwards. This is the beauty of Newton's first law. This is why I tried to tell you Newton's first is a really, when you wrap your brain around it, really handy law. This is a job for, B says draw a free body diagram. So let's do it in the white space right here. You know what? Let's do it right here. Got room. What are the forces acting on this parachutist? Get the obvious one. Okay. What else? Bigger, smaller, or the same size as mg? And how do I know? Our net acceleration is up, so there has to be an unbalanced force pointing up. And I tend to exaggerate it so that I don't. Do yourself a favor. Don't do something like this, right? Well, that's longer. You might miss that later on. So I usually really exaggerate these so it's obvious who's winning. C says write a force equation. Oh, okay. We can handle that. Malcolm, who's winning? Who's the loser? Nick, you didn't see. He looked at you. Look, he started to put his name on things now. He's not a loser. He's remembering to put his name on things now. Which the losing force? So we have this. F air. That's terrible. Make a subscript, Mr. Duick. F air minus mg equals ma. Nick, redeem yourself. Make yourself look good in front of Malcolm. What's D asking me to find? Oh, in my equation, what am I going to get by itself? Yeah. Now, I could also have given you the air resistance and said, find the acceleration, divide by m. That's really going to be, the equations are going to get bigger and more cluttered, but they're going to be that, Marley. I'm either going to give you an acceleration, find a mystery force, or I'm going to give you a mystery force and say find an acceleration. How do I get the F air by itself? Yep. What was the mass? 90? 90? What was A? Did you look for the word acceleration, or when you're looking for A, did you just look for a meters per second squared? Because that's all I did. That's got to be the acceleration. And then I went back and I checked, but that's where I targeted. So 1.5 plus 90 times 9.8. What do you get? Sorry? 1017? And then I wrote here, the force of air resistance is actually not a constant value. As you speed up, it gets bigger. As you slow down, it gets smaller. Are we speeding up or slowing down here? So what's going to happen to air resistance as I slow down? It's going to get smaller and smaller, and eventually it'll be the same size as mg. If it's the same size, what would my acceleration be? But hopefully my new velocity, which I haven't bothered trying to crunch, would be small enough that when I land on the ground, I'm okay. Yes, that did work. Bring back the longer diagram. Where was it? Dope. There we go. So I wrote here, the force of air resistance gets larger as speed increases. You may have put your hand outside the window of a moving car. Maybe you've ever done that before, okay? And you'll notice as you go faster, you can feel it pushing harder. What happens when you do this, when you turn your hand perpendicular to the ground? Okay, so it also depends on, here's your fancy word, the cross-sectional area of whatever shape. And all a parachute is, it has a much larger cross-sectional area than I do when I'm in free fall. It depends on a few other things. There's something called a drag coefficient. It actually depends on the square of your velocity. But once you reach that steady equilibrium point where air resistance and gravity are the same, we call that terminal velocity. I hit it twice. I hit it in free fall, without a parachute. That terminal velocity would have been terminal if I hit the ground. It would have been fatal. And then I hit it again after I opened my parachute. A new, much smaller terminal velocity. Put your pencils down, look up. You can turn the page if you want to. Here's a nice video looking at the physics of skydiving.
When a skydiver jumps out of a plane at 3,000 meters, her speed goes through some big changes. So what's happening to the forces as you fall through the air?
So right when she jumps, what's the only force acting on her before she's even started to move? Gravity. So she would be accelerating at 9.8. But as soon as she starts to speed up, air resistance starts to act in the opposite direction.
The force of gravity is always trying to pull us towards the Earth. Before the skydiver jumps, the floor of the plane provides a counterforce.
Oh, what is that red force? What would we call that, since it's the surface of the plane pushing up? So here we have forces are balanced, normal forces canceling out gravity.
Which balances the downward force of gravity, right up until the moment she steps out.
No more normal force. We said yesterday, this is what most astronauts feel as weightlessness. This is what you think weightlessness is, because none of you have ever been deep in outer space away from any planets where there's no gravity. True weightlessness would be if you were in the center of the universe somewhere with no planets around, then you're weightless because there is no force of gravity. But what we achieve is free fall. No normal force.
Gravity immediately pulls her towards the ground, and she starts to accelerate downwards. But air resistance is acting in the opposite direction. The faster she falls, the greater the air resistance. Eventually, the upward force of the air equals the downward force of gravity.
How fast is she traveling? How many kilometers per hour is that? Yeah, terminal velocity for a human, right around 200 kilometers per hour. Varies a bit depending on your surface area, bigger people, smaller people, but right around 200 kilometers per hour. If you hit the ground at that speed, not good. Okay, but she has hit terminal velocity.
When forces are balanced, the speed remains constant. That doesn't mean she stopped falling. It means she stopped accelerating.
And this is why I keep saying Newton's laws only tell us the direction of acceleration, not the direction of motion.
She's still doing a steady 55 meters per second, and hitting the ground at this speed isn't a good idea.
When she opens her parachute, which arrow is going to get bigger? Which way will she accelerate then? She'll still be moving down, so she'll be slowing down.
To slow down, the upward force needs to be greater than the downward force. When the parachutes open, air resistance suddenly becomes much greater than gravity. The forces are no longer balanced, and this changes her speed.
She's slowing down. Yeah, she's slowing down. Now, if you really pay attention, this is why we can't analyze this. The rate at which she slowed down was changing. This is not a constant acceleration. Her acceleration was biggest right when she pulled the parachute, and it's starting to get smaller. That we need calculus for. That's why I can't analyze it properly.
Because she's slowing down, air resistance decreases until it balances gravity again, and she reaches a much slower constant speed.
5 meters per second, what's that, about 18 kilometers per hour, give or take a little bit, so much slower.
Approaching the ground at 5 meters per second is a much better idea.
Oh, when she hits the ground, which of those arrows will change, or will they? I disagree with Parker. It's not going to be air resistance, but there still will be an upwards force. Okay, I think the ground force has to be a bit bigger than gravity to bring her to a stop. The normal force, I think we should see a brief spike.
As she hits the ground, there's a thumping great counterforce from the Earth, which decelerates her very quickly.
And then if you watch skydivers closely, and again, this we don't have the physics to analyze, you may even notice what they actually do. They stall their parachute just right when they're about to touch the ground. They change the angle of the parachute to their motion, and they try and increase air resistance just enough to even bring that 5 meters per second down to about 1 or 2 meters per second.
So for skydivers to land safely, they need to understand forces and use air resistance to slow themselves down.
Does that make sense? So, hey, let's talk about helicopters and rockets. A helicopter accelerates upwards at 2.5 meters per second squared. What lift force is exerted by the air on the rotors? Liz, what's this question asking me to find? Lift force. I'll call it, how about FL? High tech. Is there more than one force in this question? This is a job for a free body diagram. What are the forces acting on this helicopter? Get the obvious one. What else? Acceleration's not a force. It's never going to show up on my free body diagram, but I'll use the direction of the acceleration to figure out arrow lengths. Oh, FL, lift force. Which way? Bigger, smaller, or the same size as mg? How do I know? What if the helicopter wants to accelerate down? Then lift force would be smaller, okay? But let's exaggerate it. Is that okay, Liam? Okay. Liz, who's winning? Who's losing? What does winner minus loser always equal? Okay, again, as far as I'm concerned, I could either have given you the rotor force, the lift force, and had you find the acceleration. I wouldn't even need to tell you the direction because you could have crunched mg, and if lift force was bigger, you know you're accelerating up. If it's smaller, you know you're accelerating down. But for now, they gave me the acceleration. How would I get the lift force by itself? So no swappy dance this time. 5,500. $5,500 times 2.5 plus 5,500 times 9.8. And again, in this unit, we're not putting in a negative 9.8. We took care of that. If you're wondering where the negative is, right there. It's in front of the M. That's where we got the negative 9.8 in when we needed it. All right, what do you get? Does that answer make sense? Is this a helicopter? Is it a fairly big mass? Should we get a fairly big force? Yeah, I'm okay with it. I'd be way more worried if you told me 12. You made a typo somewhere, right? Oh, let's do some rocket science. Example 6. I like example 6. I like example 6. Example 6 is the next question. A rocket which weighs 12,740 newtons on Earth is launched. The force of propulsion is 15,400 newtons. Okay. Spencer, once you're done looking at your phone, what does A want me to find? A. What does A want me to find? Okay, you're back with me now? Oh, you shouldn't have been staring at your phone. What does it want me to find? Say it again, you're right. Isn't the mass 12,740? That's the weight. Okay, if they tell me the weight, how do I figure out the mass? It's really Alex's theorem in disguise. I'm going to say, oh, no, yours is getting the A by itself. We're getting the M by itself. It's going to be F divided by G. It's going to be 12,740 divided by 9.8. You get 1,300 kilograms? Okay. Cool. Aiden, what does B want me to find? Acceleration. Do you see a VI or a VF or a T? Or I think I'm going to find acceleration using forces. Is there more than one force in this question? Well, I got weight, I got propulsion. You know what this is a good job for? A free body diagram. Aiden, what are the forces acting on this rocket? Get the obvious one. And I can even put a number there, 12,740, apparently. What else? Aiden, my friend, what else? Is the force of propulsion in this question bigger, smaller, or the same size as mg? Bigger, because they actually gave me the numbers. Okay, or if they had said we're accelerating up, I would know it was bigger. So I'll call it FP, and that is 15,400. Okay, talk to me. Now what? How can I use that to find the acceleration? What equation can I write, Aiden? Oh, but I need to get the A by itself. So the acceleration is going to be 15,400 minus 12,740, all divided by, what was the math? 1,300? Do y'all get 2.05? No, yes? Yeah? Again, I hope you're trying these on your calculator. It does me no good if you don't know how to type these in. This is interesting. Look up. Don't write this down, but look up this equation here. As we burn fuel, what happens to the mass? It gets smaller. So this m and this m get smaller. What happens to the acceleration? It gets bigger. This is, I think I told you, this is why the astronauts pull their maximum G's at the top right before they shut off their thrusters. On the launch pad, they're accelerating very majestically, but they're not pulling many G's at all because there's so much mass. Now let's go to the moon. Suppose we move this rocket to the moon where the acceleration due to gravity is 1.6 meters per second squared. If we want the rocket to accelerate up at 3.5 meters per second squared, how much force of propulsion do we need from the engine? Ooh, cool. Lyle, what's this question asking me to find? Yeah. Which way are we accelerating? I think it's the same free body diagram, but with different numbers. So if you'll just be okay, can you imagine those numbers aren't there? But I think we could do another free body diagram, but I think, Lyle, who's winning? Who's losing? What does it equal? What does this want me to find? I don't think it does. I think the acceleration is 3.5. What does this want me to find? Yes, Okay, how will I get the FP by itself? How will I move mg over? Magic? Witchcraft? Or is there a mathematical operation I can pull off? Adding, you say?
No.
Yeah, you're right. You're right. I'm going to add. The force of propulsion is going to be ma plus mg. Mr. Dewick, we're on the moon. Doesn't the mass change on the moon? Or the mass does not change. So 1,300 times, Lyle, what's the acceleration? Plus 1,300 times 9.8? We're on the moon, 1.6. And this is why, by the way, if you've ever seen or watched the Apollo moon footage that's on YouTube, you'll see the rocket leaving the Earth, the Saturn V, massive. The rocket leaving the moon doesn't need to be as big. Less gravity to overcome. Yeah. I can have Silver back? Because, Silver was crying. What do you get? Can I do this one in my head? Maybe. It's going to be 1,300 times 1.9. Well, 1,300 times 2 would be 2,600 minus 130. So is it 2,600, 2,500, 2,470? No, I'm totally wrong, aren't I? Is it? No.
I got 6,630.
Really? I subtracted. I need to add. Jeez, that was dumb of me. 6,630. Units, it's a force. Newtons. Okay? Can you see that this, it's really the same as the tension going up and down equation. It's really the same as the elevator normal force. All we're saying is which way are you accelerating, who's winning, write an equation. They're all the same kind of idea. Next page. We don't always need to do a free body diagram. There is a trigger word that says, I've done the free body diagram for you. Okay? Example 7 says this: a 1,200 kilogram car accelerates from rest to a speed of 33 meters per second in 8.5 seconds. What is the net force on the car from these tires? What does this question want me to find? The what force? The what force? The what force? Everybody, the what force? If you ever see, if the question ever says net force, you can go straight to, and why? If you look at your green sheet, it's not F equals MA, it's F net equals MA. If I ever use the phrase net force, it means I did the free body diagram for you and I already added the left-hand side, combined the left-hand forces already. Okay? So, in example 7, it's the net force. I can go straight to F equals MA. Do I know M? Yes? Do I know A? Or do I? Let's be organized but lazy. What's that tell me? I'm going to write above here, VI equals 0. What's this 33? What's that 8.5? Sorry? Is there an equation for A that has those in it? What? Get the A by itself. So if you want to be technical, here is yet another equation for force. It's also mVF minus VI over T. I guess technically that's another way to calculate force. I'm not going to memorize that, and honestly, I might not even do it this way. I might actually just find the acceleration and go F equals MA. But just to let you know, any A from the previous unit, if you get the A by itself, can be put here, Sarah, and generate a new equation for force. Okay. 1200. 33. I guess since VI is 0, I could have just ignored it. Divided by 8.5. What do you get? Oh, I totally typed that wrong. 1200 times 33 divided by 8.5. You get 4,660? Newtons. Okay. 33 meters per second. How many kilometers per hour is that? What's your question? Liam, what's your question? I just did the defic right here. I could have gone like this. Right here. What's VF? What's VI? 0, so I kind of went like that. What's T? Is that all right? 118.8, which for it's a car, not a dragster. Okay, I thought I'd made a dragster question. I was going to say these are bad numbers because a dragster exerts way more force than that. But a car, no. That's about right for a small 4-cylinder. What's your homework? Every question, okay? But you'll have the rest of class. I was trying to give you 2 hours. I'm going to give you about an hour and a half because I got to go on a rant. I'm going to pause the video, though. People that aren't here aren't going to hear the rant.